Welcome back. In this video we're going to talk about parallel and orthogonal planes. Let's begin with a definition of what it means to have two planes that are parallel. And we say that two distinct planes are parallel if their respective normal vectors are parallel. This goes back to a fundamental definition, which is that the direction of a plane is the span of its normal vector, where the span means the set of all possible scalar multiples of this vector. So we say two vectors or two planes are parallel in the same direction if their normal vectors are in the same direction. Another way to say this is if we have two normal vectors corresponding to two different planes, and one of the normal vectors is a scalar multiple of the other, then we say that the normal vectors are in the same direction, and thus the planes must be in the same direction, or they're parallel. This is the definition of parallel planes. Immediately you might start to imagine, if this is what it means to be parallel, what would it mean to be perpendicular or orthogonal? Could you guess? I'm going to steal the fun away from you by giving you an answer before you had the chance to fully think about that. Orthogonal planes are planes where the normal vectors are orthogonal, which means if you look at two different planes with different normal vectors, and you were to take the dot product between those normal vectors, if you get 0 out, we would say that the normal vectors are orthogonal, and thus we classify the planes as orthogonal. Armed with this knowledge, let's do some analysis of a particular example. Here we go. Suppose we are given the equation for 4 planes, and we're asked to determine which of these planes are parallel and which are orthogonal. Here we have plane 1 is given by 2x minus 3y plus 6z equals 12. Plane 2 is given by the second equation, plane 3 by the third equation, and plane 4 by the fourth equation. Notice these are all implicit equations because the output variable z is not explicitly written as a function of x and y. We want to determine which are parallel and which are orthogonal. To do so, let's let n sub I, the vector, be the normal vector corresponding to plane I, where I runs from 1 to 4. In doing so, we notice that we can read the components of each of these from the scalar equation of the plane. In particular, if you had the equation ax plus by plus zz equals 0, we would read the components of the normal vector for this plane from the coefficients on the x, y, and z variables. In this case, we would say this has normal vector a, b, c. Once we recognize this, and that comes from the dot product definition of a plane, remember the whole idea, I'm going to just come back to this over and over and over again to encapsulate where this formula comes from. The whole idea in a plane is that we have a known point in our plane, we have a general point in our plane, we connect a vector from the known point to the general point, and we say we want to collect all general points such that this vector is orthogonal to n, the normal vector of the plane, which actually correlates to the unique direction orthogonal to this plane. And then this correlated with this vector equation, which was if I take the normal vector dotted with any vector in the plane, I get 0. And when we actually looked at the scalar coefficients here, we saw that a, b, and c came from this. Once we have this intuition, we can go back to each of these planes and define the normal vectors. In this case, we say that n1 would be the normal vector for the first plane, and notice that would be given by 2, -3, 6. When we go on to n2, which is the normal vector for the second plane, we see that this would be a -1 in the first component, 3 divided by 2 in the second component, and -3 in the third component. n3, the normal vector for plane 3, would be given by 6, 8, 2, and finalmente vamos a decir que the normal vector in the fourth plane is -9, -12, -3. So now we have the vectors that encode the directions of each plane. And we can notice something quite interesting. To get from 2 to -1, I would have to divide by -2. So if I were to look at n1 times a -1/2, this would be -1/2 times 2, -3, 6. And we notice that we would get the vector -1, +3 over 2, -3. And this is exactly n2, which says that -1/2 n1 actually gives n2. And the moment that we see n2 is a scalar multiple of n1, this implies that n1 and n2 are in the same direction, because remember, direction is defined to be any scalar multiple of a vector. This is a very special definition of the word direction in Math 1C. Once we have the two normal vectors in the same direction, we can conclude based on the definition that planes 1 and 2 are parallel. Similarly, we could note that when we look at n4 and n3, if you divided this by a -3 and multiplied by 2, you would get to 6. So here we would say n4, I'm going to go ahead and divide this by 3 with a negative on the 3 and multiply by 2. This would be -2 over 3 times, I should put this up a little bit, 6, 8, 2. And of course, when we go ahead and do this, 6 divided, oh, sorry about that. -9, -12, -3. When we divide this, we would get something like -3 times -2 is 6. -12 times divided by 3 is -4 times -2 is 8. And then the same thing here, we would have something like +2. And this is exactly n3, which implies n4 and n3 are parallel, which implies plane 3 and 4 are parallel by definition. We've now confirmed that we know that planes 1 and 2 are parallel and planes 3 and 4 are parallel. The last thing that we're going to do is investigate whether or not any of these planes are orthogonal. To do that, let's take a look at the normal vector, since that allows us to check orthogonality quite quickly. Finally, we notice that if I take n1 dotted with n3, okay, this would be 2, -3, 6, and I'm going to go ahead and dot that with 6, 8, 2. Because I am tired right now and I don't want to make a mistake, I'm going to go ahead and write this out fully. So here we have 12 minus 24 plus 12, and indeed this is equal to 0. The moment that I know the dot product between n1 and n3 is 0, this implies via a theorem that n1 is orthogonal to n3, and the moment that I know that n1 is orthogonal to n3, this means that plane 1 and plane 3 are orthogonal. And I can actually conclude immediately that that also means that plane 1 and plane 4 are orthogonal. And I'm just going to go ahead and remind you why that might be true. Remember that we had said that n3 was a scalar multiple of n4, which immediately means if I took n1 dot n3 and I were to get 0, then, well, if I just go ahead and substitute, this would be alpha times n4 equal to 0, and this alpha was non-zero, right? Okay, and this would mean immediately that alpha times n1 dot n4 equals 0, but I know that alpha is non-zero, so this must mean that n1 dot n4 is equal to 0, which means n1 is orthogonal to n4, which means plane 1 is orthogonal to plane 4. And the way to think about this is a lot of math, blah, 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 blah. If plane 3 and plane 4 are parallel, and plane 3 is orthogonal to plane 1, well, it must be that plane 4 is orthogonal to plane 1. This is the algebra to back that up. Of course, if plane 1 and plane 2 are orthogonal, this means that, plane 1 and plane 2 are parallel. The final thing that we can say is plane 2 is orthogonal to planes 3 and 4. And we're done with this example. I'll encourage you to graph this in Mathematica if you feel so excited about life and math. I'm going to go on to the next example so that we can get into a more interesting case of how to use Mathematica to visualize planes. This one would be a repeat of the stuff that we did in the last video. Ready? Here we go.